Hi, what's up YouTube? My name is Abhishek. And if you're studying physics for a while, I'm pretty sure you've wondered why the velocity of light has to be constant. Well, in fact, it was the Einstein's postulate of relativity that said that the velocity of light will have to be constant regardless of the frame of reference of the observers and regardless the motion of the source of photons. So it's a very profound scientific notion because it not just goes into the realms of physics, but it goes apart from there and enters the realms of philosophy. And it gets kind of philosophical at some point because um, this concept really questions the events happening around you. And it really all it proves, the velocity of light being constant and velocity of flying being the ultimate velocity, it only makes a lot of sense because it tries to cry out that the events that are happening around you cannot be changed because you're perceiving those events with the help of photons. And those events can only happen in one way. And no one can see the events happening in a different way, even though that person is moving at a very high velocity, even close to light. And it does make a lot of sense again, because if you cross the velocity of light, then every notion that has been made, every theories that we have created, let it be special general relativity or quantum field theory, they have a proper constant velocity of light. And each and every theory would be just wouldn't make any sense if we have introduced anything that has a velocity more than light. So let's try to see one example out of it.
So this is our first frame of reference, where our observer is watching in his spaceship traveling at some velocity 1 million meters per second. In his little device, this photon is going back and forth from one point to other point and bouncing or reflecting back and forth at a distance, we'll call it x later. So the only motion this observer is watching for this photon is back and forth in one dimension. But now let's see what this observer watches. And this is our second frame of reference. Now you can clearly see what this person in the rest is observing about the same device that was in the rocket before. The photon is not just going up and down, but it's also following a different path. This is not a sinusoidal path, but this is actually a straight path with defined angles and a similar slope. So now this photon is not just going up and down, but it's also going diagonally to cross the points, upper and lower points of this device, um, to collide with the upper and the lower points at the same time interval. So both the observers are going to observe that the photon will hit the point at the upper and the lower part of the machine. Both of the observers will agree that the events occurred, but both of the observers will not agree on the time when this event occurred. Now, the speed of the light is similar for both the observers. That was our prime argument. Now, the speed of the light is similar here, that is c, but also in our previous animation, the speed of the light is still c. And that is when we have to argue that there has to be something different since the velocity is same. Let's see how.
So this is what I meant by the by that kindergarten nursery rhyme animation you just saw. This is my first observer and this is my second observer. First observer is watching the photon to go from point A to point B in pure vertical motion. So I'm going to go ahead and I'm going to assign the value of photon as c right now for both the observers, because that's the postulate that says that the velocity of light has to be constant regardless the motion of source of light and regardless of any inertial frame of reference. So my velocity is c. Let's also assign a value um, for the separation of mirrors. Let's say x. Here it will also be x. And let's now assign the time period t, which is the time that the photon takes to go from point A to point B. So my capital T, let's assign capital T here for S frame of reference, which will be x over c. And that's all we know literally. But in the other S prime frame of reference, the observer is trying to watch the system, the mirror system, moving forward with a constant velocity. So that means let's also assign a constant velocity v to the mirror system. And that's why the time period is going to change, because the photon trajectory here is actually, photon covers more distance to go from point A to point B. And that's why the time taken for the photon to go from point A to point B is going to be more for S prime than S. Because remember, again, the velocity of light is constant for both. That's why we have to make the compromise with time here. So this displacement will be for the mirror will be since we know the velocity is v, so this will be v times let's assign value tau for the photon to go from A to B in S prime. So this displacement for the mirror system will be v times tau. And now I can just use Pythagorean theorem to make sure to calculate the displacement, actual distance traveled by photon in one time period tau. So this will be square root of, let's try to do some trivial math here, square root of x squared plus v squared tau squared. And since now we know this distance, well, I can also calculate the actual time tau with respect to the displacements that we just calculated. So my tau will be this displacement. Also, of course, the velocity of light is c x squared plus v squared tau squared divided by c. And I can just take the square roots out and say c squared tau squared equals to v squared tau squared plus x squared, or c squared minus v squared times tau squared is equal to x squared. But instead of x, we're going to cheat and move our way ahead by saying x is c times t according to this frame of reference, because x is same too. That is the separation between the mirrors. So I can write x squared as c squared times capital T squared, and here we get a very important relation between the time period of the photon to go from A to B for S frame of reference and the time period for the photon to go from A to B in S prime frame of reference. So now it's just a matter of minutes where we can just calculate the relation between the tau and t. So my t squared will be equal to tau squared times c squared minus v squared over c squared, and that's it. Well, I can also simplify this equation and try to derive gamma for you. So gamma alert. T squared, I can also remove the square roots now. T squared, t equals to, or let's be more precise here. The time taken by the photon to go from A to B for S observer will be the time taken by the photon to go from point A to point B for S prime observer times. So I can put square root of 1 minus v squared over c squared. So this is a very trivial calculation, so I don't have to go into the coordinate systems to assign a coordinate and assign a different frame of reference and then try to derive the Lorentz transformation. But instead, this simple example tries to prove that if you consider the velocity of light is constant, well, that means the photon is gonna just take more time to go from one point to another point for some observers compared to some other observers. That's all it says. And now let's try to analyze this equation further. And I will try to explain why the velocity of light will have to be constant to actually maintain the events, to actually maintain that the events are happening. Let me explain more clearly. Okay, so we have covered a lot of stuff, but I still owe you an explanation about why the photon's velocity has to be constant every time. So, first rule of thumb is that both the observers are going to observe the photon hitting the point B at some point, reflecting back at some point, hitting point A again at some point, reflecting back at some point, and so on and so forth. And this explanation just, well, this is very important to understand because that's what governs the events happening for both the observers. For both the observers, events are gonna happen the similar way, regardless of the time that has been experienced by both of these observers. So now let's try to assume that the velocity of light is not constant. In that case, we are just saying that the time taken for the photon to go from A to B for this observer will be equal to the time taken for the photon to go A to B for this observer. So both the values are t. And that means photon has to cover more distance, of course. And that means photon gets higher velocity because of the velocity of this source. And that is not possible because the velocity of the photon should not be governed by the velocity of its source. So if the photon attains a higher velocity than itself, than compared to this, then that simply means that photon is actually here not gonna hit this mirror in the first place, because photon has a higher velocity, and this velocity is like some constant velocity v that we are giving to the system. And that means photon actually, for this observer, remember, still for this observer, photon is going back and forth. But for this observer, photon never hits point B and just deflects off from the mirror. And that is just utterly impossible and very hard to try to try to get your intuition on, because photon has to cover the distance from A to B and has to reflect back for this observer too. So if we consider any light or any velocity that is higher than photons, that means you're actually breaking the events, breaking the happening of events between the two observers because of the non-constant velocity of light. Don't believe me? I promise it won't take lot of time. So let's assume, again, let's try to prove this thing mathematically. Um, so t is equal to t, and this is equal to c. I know this is equal to x. So my x will be c. Okay, let's now, since we are assuming different values of photons, this will be c1, this will be c2. Clear? So my x will be c1 times t. And this distance will be equal to, now let's still assume we have a velocity v, and let's assume we still have the same time period t for both the observers. So now again, this distance is v times t, this distance is still x, so I can say this is square root of x square plus v square capital T square, again capital T square because t is same. And that's why I can say that this velocity, since we just calculated here, x is c1 times t, so we can say this value is actually equal to c2 times t. Remember, again, t is the same thing. T is the similar time we have here. So I can write, t is equal to x over c1. So I can write this t, sorry for taking shortcut, but I don't have much space remaining. So x over c1. And I can just take square roots now, I guess. X square plus v square t square equal to c2 square x square over c1 square. X square plus v square t square, so x is my c1 times t, so c1 square times t square plus v square t square is equal to c2 square x square over c1 square. So let's try to take t in one place. So t square, c square plus v square will be equal to, well, I can still write x as c1 times t. I don't know why I did that before. So my x square can be c1 square t square. C1 gets cancelled. Okay, I hope you can see this though. So now I can cancel the t and t. And in the end, you can do this calculation yourself because it's very trivial. C square plus t square, c square plus v square is actually equal to, alright, no, wait, hold on, this is c1. So c1 is the velocity for this observer. So c1 square plus v square is actually equal to c2 square. And that means you're actually trying to derive the velocity of the photon for this observer with respect to the velocity of the source of the light and the rest velocity. And that means that the events, or that means that this observer will know, or this observer here will know that he's in motion because he can calculate the velocity of photon to be completely different with compared to someone else. So that means this observer, and that shouldn't happen in physics. Like when you're in a constant velocity, the laws of physics should be equal for you. Everything in this universe is moving with constant velocity, and the laws of physics are still similar from all the observations. So that's pretty so that intuition should get shot down in your head right now. So basically, you have an ultimate velocity of photon to make sure that the events happen for both the observers. Again, photon would actually not hit this mirror in the first place if you try to observe a higher velocity of photon. So that's basically it. I mean, you should have a constant velocity of photon to just make sure that the events keep happening the same way, even though the time periods experienced by both the frame of references may be different. So that is it. So I hope you're able to understand the concepts of time dilation and the velocity of light after this video. Again, in the end I would say that the velocity of light is considered constant by the scientific community to make sure that the events observed by two observers in different inertial frames are the same. So both observers moving apart from each other with a constant velocity, they should observe that event happening there. Even though those events happen differently, or those events happen at different times for both the observers. And that is why the velocity of light will have to be constant and ultimate to make sure that there is no distortion in any events. So, that was it for this video. If you have any doubts, please let me know in the comments and I'll answer you. I'm Abhishek, this is the Physics Sir. Thank you for watching.